Okay, just a quick overview, and then we will move forward because we are almost done with or getting to a closure of the classification problems. So just wanted to summarize. All right. In the meanwhile, if anyone has any questions, probably we can discuss them as well. See, basically, over the last few sessions, we were actually talking about the supervised learning algorithms, where our objective was to do a prediction of a category. What was that category? The category was whether a person will default or not default. So this is what was our objective, to predict whether the person will default or not default. Now, to do this exercise, we have taken a data set called loan default mini. Right? I'm just giving an overview. Anyone has any questions, we can discuss on that. So we were given an objective to predict whether a particular person will default on a loan or not default. So to address this problem, we have taken this data set because this data set contains so many variables associated with a person, along with historically whether a particular person has a defaulted or not defaulted on his or her loan. Right? So our objective in a supervised learning algorithm is to fit a kind of a relationship between y, which we have called as our target variable, and different x values, which we are calling them as feature variables. So I want to fit the best possible relationship between x and y. Okay. So how do I build that best possible relationship between x and y? So for x, initially we have done a lot of data cleaning activity. So if there are any missing values in the data, we try to identify all these things. If there are any outliers in the data, if there are insufficient number of observations in the data, etc. So there is a lot of data cleaning that we have done. Then after that, we have entered into the process of data pre-processing. So wherein we try to scale the data, we try to do some kind of non-linear transforms. Then we also entered into feature selection methods. So like that, we have applied a few more things on the data. And after we did all these things, we went ahead applying different algorithms. Algorithms are nothing but different functions. Each algorithm is targeted towards building the relationship between x and y. So we have looked at so many algorithms. Initially, we started off with perceptron. Then we looked at logistic regression. Then we also moved towards the other ways like KNN, decision trees, random forest, gradient boosting, naive Bayes, support vector machines. These are the various kinds of algorithms that we have looked at. Probably I am also going to look at the artificial neural networks now, which is otherwise we are calling as the multi-layer perceptron. So what are we saying? I can vary. So basically, what is the relationship between X and Y? After X has been cleaned, pre-processed, etc., what is the best fitting relationship between X and Y? So let's say if this algorithm comes out to be the best fitting relationship. Now in finding out this best fitting relationship, what did we do? We tried to check. We tried for all these things, the mechanism is the same, right? And in all these cases, I have come out with a pre-written piece of code, which is very, very important because at the end of the day, I don't want making mistakes in the classroom in terms of the syntax issues and all. So there has been a pre-written piece of code. We are running that piece of code in the class to understand the output. The output is already pre-run so that we can understand what is going behind the scene. Now, in each of these algorithms, the mechanism that has typically been used is more or less similar. We have been using the scikit-learn library, and this scikit-learn library has a fixed format in which all these algorithms can be used. So we have gone into the writing of the various algorithms and running them. So for you, this entire thing would become more and more easier if you take some other data set and do the practicing of these algorithms on that particular data set as well. So you have to do one end-to-end practice by taking a new data set and trying to understand each and every line. And wherever you are getting stuck, I think we should be able to discuss them out and we should be able to resolve that particular issue. All right, so we are done up to here right now, right? We have taken up the supervised learning algorithms. So one category is predicting of a category, which is what we have called as a classification problem. The other side is predicting a numerical value, which is what is called as a regression problem. So regression problem also to a large extent will be more or less similar to a classification problem. So we will quickly look at a regression problem also. We don't need to discuss much on it. I will take one example. I'll run you through that entire example, right? So that the overall process, there is not much of a difference between classification and regression. Wherever there is a difference, I will try to highlight on that particular difference. So in this process, so wherever there are some queries, we can spend some time on those things, right? This is the entire process of doing a kind of a classification exercise. So wherever you think there is a gap in the understanding, probably we can spend some time to discuss that out, right? Because somewhere I'm seeing that some of you are not comfortable with the typical class. So just wanted to understand where the gap is so that if possible, we can try to address it. So obviously there is an effort that is needed from your side as well. But if there is something else that I can focus on, that can actually help me. Okay. Yeah, gaps. See, first let's understand, Dave. I mean, we are all professionals. We are. After that, there is. So when is that gap you are referring to? The last week, the GCA week, or okay? I mean, what is lacking? Can you just give me? See, I have already given you an exercise, Paras. I have shared the data sets with you, and I asked you to do parallelly whatever we are discussing. See, I asked you to do the exercise parallelly on a couple of other data sets. I've already shared 2 or 3 data sets with you, probably from the insurance and financial domain itself. So I really want to understand. I mean, of course, the subject wise, initially the subject was much lighter, but as we move, the subject is becoming more heavier. But see, more or less, we are in a virtual this thing, so everything has to be individual driven. So exercises typically, according to me, they are more of individual driven kind of thing. So you should do the practice, and wherever, let's say the code is slightly not working because of whatever reason we are trying. I'm trying my level best to ensure that there are no issues with the code. But because you have taken a new data set and somewhere you are getting stuck with the code, obviously you should come back to me. Okay. Definitely. I mean, when we are doing 3 sessions in a week or something, there might be a little bit of load. But at the same time, some cancellations are very much possible because we all are working professionals. This is not my only duty taking the class out here. So basically, we are all professionals. So which means some cancellations from my side, from your side, very much possible, right? We have to understand that. And I'm really not sure because some of the people have written a kind of a feedback that this course is completely useless for them. So I'm really not sure what is going on. So that's the reason I thought, at least for people who are attending, where is the gap so that we can try to address, right? So my feel is probably we need to do some kind of a practice. So if you say that probably some kind of practice on a couple of other data sets, you would like to do it parallelly and take a small break and then we come back after some time. I'm not sure, but again, I want something from everyone. So probably some of you, if you can let me know. Obviously, I am seeing that some gap, if at all, but I'm really not sure. Yeah, but I think I mean, only a few people getting a benefit and others finding it very much problematic. Somewhere, I think. So practice, obviously, now you have the codes available with you, right? I mean, what I simply say is now you have the codes that are available with you. So, which is like a ready-made spoon-fed kind of thing. So, in case you want to do it at the later exam, is it possible to postpone this course till May exams? I'm really not sure because we have almost come. I mean, probably we may still have some 5 or 6 sessions at the max. So by end of the March or just in the first week of April, we should be able to complete, because the remaining topics, they are all like introductions to the various areas, introduction to time series, introduction to natural language processing, where my intention was just give you a brief overview of each of them. So one class for each of them is what is the target. So the major chunk, which is the machine learning, I think in another couple of classes, we should be able to wrap it up. So you can plan out with IAI. You can write to Ravindra, and probably if everyone in the group is fine with it, I don't mind, because for me, it does not matter. I mean, some cancellations can come here and there, but more or less, I should be able to take my time out, right? And so that's what it is. So probably whatever is the way, probably you can discuss on a larger platform with Ravindra and IAI, and accordingly we can take out. Okay. But yeah, I mean, my only request is anything that is not clear, please get back to me. I don't know, different people are there at different levels of learning in this batch. So definitely, I mean, just without knowing where you are, I don't think I can categorize to everyone's requirement. So if something is not clear, just like our friend Dave and all are highlighting sometimes. So if something is not clear, obviously you can come back to me, right? So you should do some practice. Obviously, no one will become a Python expert at the end of the day. Even today, I may not be a Python expert. See, but the advantage of Python and R typically is you can Google them out. So you can find code everywhere. But how do you link all those pieces of code to create a solution is the most important thing. And that is where we are focusing on. And along with creating a solution, how do I analyze the output is another important thing. And that is what we are typically focusing on. So regarding the code, you have to run. You take another data set. First, try to run with our own data set. And if something is not clear, then better use, if something is not clear, get back. If everything is running fine, take another data set, similar problem, but with a different data set. See if you are able to make the necessary modifications in that code. So if you are able to make the necessary modifications in the code, it is very much fine. I mean, you are decently good. You, in many cases, you will not write the code right from scratch. For solving any problem, you will not write the code right from scratch. You will be taking help of some code that is already existing. So as long as you know where to look out for and how to look out for, I think that should still solve the problem. So being new to Python, probably you have to run the initial few codes that I have shared with you, right? So this code which we are using, I think for the last few classes, the classification data set, this is what we have been using for the last, I think 8, 9, 10 classes at least. The intention is an end-to-end case study. This is an end-to-end case study where my objective is to do a prediction, right? So what all we are going to do. So what you should do, run every step and try to see what is that this particular step is doing. And wherever something is not clear, you can very well get back to me. So that is what is the typical expectation, obviously, because different people are at different layers of understanding. Sometimes it might create a problem, right? Some of you may be just wanting only to know Python. Some of you may want to go towards providing a solution. So depending, so basically we have very clearly shared at the beginning in terms of what all are going to be covered as a part of this curriculum. So if there are any, obviously the number of classes that we are taking is much more than what has been specified in that curriculum. So we have not deviated anything from the curriculum till now, but we have gone for more classes than what we have initially communicated, because some of you are very new, and because of that I could not go at a faster pace when it came to a few of the initial lectures. So now definitely, I mean, you by now you should be quite comfortable in terms of executing each of these things. Of course, here most of the times I mean, I always see that in this professional world, we should be self-motivating ourselves. We should go ahead. Whatever we have discussed today, probably before the start of the next class, you should be able to practice them, and you should come back with the doubts, right? Probably that is something that where you have to motivate yourself, because you have enrolled for the course. You have to come out with respect to the doubts, etc. So what I somehow feel is, the more and more self-motivated you are towards any learning. In my 20 years of teaching career, that is what I typically believe in, right? Whatever the topics that I teach, I always try to communicate the concepts clearly, but obviously different people are at different levels of learning. So it has to be a motivation from your side. It has to be a kind of a drive from your side in terms of asking different questions. So I am very much open, whatever you would like to come back, right? Obviously, you have the code sets with you. So you can very well work on a new data set, or first of all, work on our existing data set itself. And based on that, see to what extent comfort is there, where you are actually losing out. And probably we can very well discuss on that aspects as such. All right. So if there is anything that we can communicate on, or whatever is the gap right now, if right now something can be addressed based on whatever the high level overview that I have given, I think I can do that. Otherwise, we can get into our today's session. Okay, benefit of naive Bayes. I think in the last class I just spoke about it. Naive Bayes compared to other methods of classification. See, naive Bayes, first of all, is very fast towards execution. I think I have covered it in the last class. Okay, you could see here. It is one thing is it is very simple, because it is based on a simple Bayes theorem, right? So that way, it does not require too complex relationship between X and Y, right? The relationship between X and Y is a very simplified kind of a relationship. So you can just use your Bayes theorem to build the relationship between X and Y. And because of that reason, it is more and more faster to implement. right? That is definitely, because especially if you are actually working in a live solution, real time kind of a solution, obviously that becomes very important. How much time is my model taking to execute? And here probably I can also talk about, so basically we can say it is fast. It is very simple to understand because it's a simple Bayes theorem. And I can also talk about even the data, if it is very small also, I can very well use it because it is purely based on probability, right? Whereas some algorithms like support vector machines and all, they require a large volume of data. So even if the data is very small, because it's a probabilistic kind of a learning, even for smaller data, we can very well use this concept, right? And if my data is whatever, so even if there is a textual data or even if it is a categorical data, etc., also it can very well work. And as we have already talked earlier, it assumes the independence. Of course, this might be a kind of what you call limitation, right? But still, even if there are large number of predictor variables, it can still be a decent solution. So because of that, especially where we are interested in a real-time solution, this could be one of the most comfort. But obviously, if the performance of this model is not that extraordinary, then probably it may not make the cut as well. So only if the performance is decently good, but at the same time, right? But at the same time, I mean, be like in the top three models or something. And because of that, though, I mean, the other two models, let's say they require too much of a time and too much of computing resources, etc. In that case, I can take a call on this particular model. So that is how you can very well look at. Okay. Fine. Anyone else? Any questions? Okay. Then I'll move further. Okay. So let's move to the next topic, which is otherwise called as multi-layer perceptron. Or in short, you can even say the general family is nothing but your artificial neural networks kind of a family. So all these will come under the artificial neural networks category of data. Now this artificial neural networks is built on the top of the basic perceptron that we have done earlier. Right? So what did we talk of in the perceptron? We simply said these are the different inputs. So I say x1, x2, x3, so on, xn. These are the various input variables. right? So these input variables, they come together. So there is some kind of weights that are applied to each one of them. And there is a summation that happens. And of course, these x1, x2, x3, xn, they are all scaled variable. So we have already done some kind of a z score or something like that on these variables. Now, based on this, there is so basically here, by the time it comes here, it becomes w1 x1 plus w2 x2 plus and so on wn xn. So this is what is going to happen at this stage. Now this value will be compared. So it will be exposed to a this will be exposed to a simple uh, sine function kind of a thing, where simply said if this value, so it's a simple step function also you can say, if this entire value is less than 0, the output will be taken as 0. If this value is greater than or equal to 0, the output will be taken as 1. So you can very well say there is a step function that comes in here. So either the value will be a 0 or the value will be a 1. Now based on this, I can very well calculate the error, because there is a actual y value also that is there. So these two are compared, right? Here this is my predicted by using these weights W1, W2. These are randomized weights, and based on that the error is known, and this error is actually playing a role in terms of updating these weights. Right? Based on this error, we use a mechanism called gradient descent. We discussed about this approach. And based on this, the error would be updated. So this is what we called as the basic perceptron. Now, all we are talking of now in the neural network kind of a mechanism is we are extending the same. We are extending this model, and probably the neural networks are much more important for the simple reason. Okay, so let's talk about this. We have the same inputs, right? We have x1, x2, x3, so on, xn. Now, what is happening is, so there could be multiple nodes here. So here there is only, earlier we had only one node there. Here there could be multiple nodes. So which means there could be multiple weights that can come. Right? There could be multiple weights that can come. So what is happening here now? So probably this node, let's say we call it as Z1. So Z1 may become W11X1 plus W12X2 plus W13X3 plus so on W1NX. This is what is becoming Z1. Z2 is also having a different set of weights. W21X1 plus W22X2 plus W23X3 plus and so on W2NX. So what is happening at each node? right? There could be, let's say this could be ZP. So there are P observations or P nodes in this hidden layer. And finally, my output layer is still finding out whether my output is going to be a 0 or a 1. But what can very well happen? Again, there could be one or more layers. Again, there could be one or more layers like this. Right? Again, there could be one or more layers. And finally, these all could come like. So this kind of transmission, which means there is a lot of transformation of the original data that is happening at multiple levels. There is a lot of transformation of the data that is happening at multiple levels. So this is what is typically called as an artificial neural network. Artificial because it is the way typically the brain functions, not getting into that aspect, but typically what is happening is it's a stage-wise processing that is happening. So first, what is going to happen now? How is the information typically passed? Let me see what. It is not a single layer perceptron. Yeah. So you could see here, Paras, if there is only one hidden layer, you can very well talk about it as a single layer perceptron. But if I am typically going for multiple layers, right? Probably we have multiple layers out here. So we can very well go with a multi-layered perceptron. Multiple hidden layers coming into picture. So this is what is my input layer. This is what is my output layer, because here in my output, I only have a 0 or a 1. Right? If this is my output layer, probably we can very well, so you can very well bring in a 0 or a 1 kind of a layer. So you can very well connect each of the inputs. So a kind of a complex network like this can very well be built. So what is happening here? So this is what we typically call as the artificial neural networks, or sometimes people use the word simply neural networks. So we are simply using all these connected nodes. Right? All these nodes are connected nodes. So here, the more and more hidden nodes, hidden layers that you are bringing in, that is where your study will move from machine learning towards the deep learning. That is where the study will typically move from the machine learning to the deep learning. Now, what are all the various things that are coming as a part of this scenario, if you see? Yeah. So in a regression, this node will be your value. That's it. In regression, there is one single node here in the output, which is what is your value. So, so you can very well treat it for regression. You can treat it for multi-class classification. You can use it for any purpose as such. Because at the end of the day, the tree can very well, I mean, I don't say it's a tree, it's a network. So the network can very well be applied for any kind of your problem as such. Okay. Probably when we are doing it in Python, obviously it's a scikit-learn library. So more or less you will find a similar kind of a pattern. So basically you can say there is an, if you are talking of simple artificial neural network, you will simply have one input layer. You will have one hidden layer with any number of nodes, and you will have one output layer, right? So, but when you are going with a multi-layered, you will typically get more of hidden layers out here. So you will get more nodes in each hidden layer, right? Which means data is passing from this layer to these layers and finally linking with the output, right? You will have all kinds of permutations and combinations. Data is going all the way from the input layer via the various hidden layers, and from there it is reaching the output. Whereas when you talk about a basic neural network, the first layer will be your input layer. So this input layer actually contains all the inputs x1, x2, x3, whatever are your input variables that are there. So these, from here, the values come to the hidden layer. Let's say this we call as a Z layer. So as I told you, Z1 will be nothing but W11 times X1 plus W12 times X2 plus and so on W1n times Xn. So this will be my Z1. This is the first node. Let's say this is my second node, Z2. Z2 will be W12 times X1 plus W21 times X1, W2 times 22 times X2, so on, W2n times Xn. So like this, let's say this, in this node I have Zp. So again it becomes Zp equal to Wp1 times x1 plus Wp2 times x2 plus and so on Wpn times xn. So this is what we typically have. Now what will happen before the values go to the next layer? There will be an activation function that would be applied. Right? What is this activation function? Some nonlinear transformation. The activation function is nothing but some nonlinear transformation. So sometimes we have the activation functions which are like, let's say, sigmoid. Now, when we are saying a sigmoid activation function, so my Z1 will be transformed to 1 by 1 plus e to the power minus Z1. Or if I have something called hyperbolic tangent kind of activation, Z1 will be transformed to, right, probably e power minus Z1 e power Z1 minus of e power minus Z1 divided by e power Z1 plus e to the power minus Z1. So some such kind of a transformation is what we call as a hyperbolic tangent kind of a transformation. Similarly, you have the other kind of transformations which is called rectified linear unit. So this is more like if the value is, if Z1 is lesser than 0, then it would be taken as 0. But if Z1 is greater than or equal to 0, it will be taken as Z1 itself. So like that, there are different activation functions. Now you will choose your own activation function at this layer, right? So which means my Z1 will be transformed to Z1 dash because of this transformation. Z2 will be transformed to Z2 dash, ZP will be transformed to ZP dash. Now again the same process. Let's say this column, the second hidden layer is W layer, or no, W is we have already used for weight. Let's say this is the A layer. Then again I can say A1 is equal to, I can set some other set of weights here, right? So let's say the weights are W. So we may have to take another set of weights. Let's say P is the set of weights. So P11 Z1 plus P12 Z2 and so on, Z2 dash. So plus and so on. So like this, what is going to happen is multiple equations are going to come. And by using, so which means there are so many parameters. These are all the parameters that we have to determine. We don't know. Initially, we randomly took some kind of parameters here, but we have to find out the optimal values for all these parameters. So there will be an error function, and that error function has to be minimum. So all these connections are typically called as weights. So if you have a multi-layered, so let's say we have 10 input values. My first hidden layer contains 5 nodes. My second hidden layer contains 5 nodes. My third hidden layer contains, let's say, 3 nodes, and my final layer contains 1. So what is happening at each layer? So here you have 50 different weights. Between these two, you have 5 into 5, 25 different weights. Between these two, you have 5 into 3, 15 different weights. And between these two, 3 into 1, 3 weights. So basically here, 75, 90, 93 weights is what you may have to find out, along with the constants as well. So your number of weights are going to cross even 100. So all those parameters have to be determined by doing a kind of, so the gradient descent itself, the gradient descent mechanism will be used to find out all those weights as such. Right? So this is where the overall functioning of the artificial neural networks come into picture. And of course, this is the base for your deep learning also, because when the number of hidden layers is becoming more than 1, the kind of learning we are talking of is called as the deep learning. Right? So we are learning from the inputs based on the relationship. So this is the way the relationship is built between your input variables and the output variable. So you could, if we can quickly summarize this, the input node, this one, is taking the information from your raw input that you have got. We have already done the transformation of that data. We have done the scaling. So that is what is the input that is being taken. So each node is having some value. And we have all of them are coming together to have a kind of a summation. On that summation, there is an activation function. So there is a weighted sum that is happening, and on the weighted sum, there is an activation, that is activation function that is being applied. So this function, for each of the new neurons that are there, new nodes that are there, that activates. So that's where it is becoming Z1 dash, Z2 dash, and so on. Right? And which means that value will be passed on to the next layer. And that's how every layer will get updated until your output layer. So this activation, whatever we are giving as our activation function, we can select sigmoid, tanh, relu, and there are a few more kind of activation functions as well. Until you reach the output value, you are going to execute that, the same process. So if there are multiple layers, obviously, multiple transformations of the data is happening until you reach the output. So, and obviously we have our error function. In this classification problems, we already know our error function. You can very well talk about y times log y hat plus we have discussed about this error function 1 minus y time log 1 minus y hat. So minus of this. So this is what we have already talked about as the error function. So based on the minimization of this error function, we try to work out backwards in terms of adjusting the weights. So there are so many weights depending on how many layers you have and how many nodes you have in each of the layers. So overall, my objective is to do a minimization of the cost function or the error function. The lower it is, obviously, the better it would be for me to execute it. Right? So obviously, the more of mathematics of it, I mean, how the weights are updated. Obviously, earlier we discussed. We take the derivative of this, and whatever is the derivative, I multiply that derivative with a small value called a learning rate. And accordingly, I multiplied with the x values also to update the weights at each of the layers. So that is how you can typically take. Of course, in some cases, we are only going in the forward direction. Whereas in some cases, there could be a lot of learning that can happen in a kind of a reverse direction as well. So that is where probably today the artificial neural networks and the deep learning kind of models, they are having a good mileage in the typical industry. How to train? Yeah, this is where, as I told you now, the error has to be minimized. Right? So which means you trace back. So in this earlier scenario, right, you have come until this output. Now you compare this output with the actual. You compare this output with the actual. So now you use this error function, right? So based on this particular error function, you know there is an error. So you go stepwise. So you can very well go stepwise backward. And based on this, you can update at each of the layers, because at the end of the day, what we are saying is obviously this y should be minimized with respect to the x, right? So obviously if it is as good as, so if you just see my derivative of the error function with respect to the x. So basically here, so I need to change my weights across all the layers so that this will overall change the y. So what will happen based on this loss function or the error function, log loss function, which is the error function, I can very well update the weights out here. Earlier, when there was one single layer of updating the weights, we talked about it, right? So whatever was the derivative, which is nothing but, so you can very well look at this log loss function. Based on this log loss function, whatever is the derivative, you can very well take that error, which is what is nothing but y minus y hat. So this y minus y hat times the x value. So in this case, the x value will be this layer first. First, you will update this layer. So you will take your y minus y hat, you multiply it with the x value, and you multiply it with the learning rate. So based on this, the new weights at this layer. So here you have these new weights coming up. So you have your weight N1 dash, weight N2 dash. So some new weights are coming out here. Similarly, you will work between these, right? You know what is your y minus y hat. So accordingly, you will work backwards to update all these weights. So that is how the training process keeps continuing. Does that make sense? So there is information is going from the input to the output. Error-based learning is happening as a reverse process. The error-based learning is happening as a reverse process, which is what is typically called as back propagation. So because there are so many variables in the process, for us, your further follow-up question, any? Okay. So typically what is happening is because there are so many variables that are getting created, so many layers that are getting created, it's obviously that I can't solve this problem using a pen and paper at all. Right? And that is where these kind of models are typically called as a black box kind of model. Very difficult to understand and interpret. So that is where we generally say in problems where the interpretation is very much required, these kind of models may not be that preferable. Because you can't give a kind of an explanation. You have so many layers, so many weights. Which one do you explain for what? So it is very, very difficult to give proper explanation of how you have determined the output. So it is these kind of models, they are generally called the black box model. So somewhere for those applications or for those models where the explanation or interpretation of why this particular person's loan is rejected or why this particular person has defaulted, what are the drivers? Probably it's not that easy to explain, right, using these black box methods. So these are some of the major drawbacks that you can always think of. Obviously, because there are so many nodes and so many weights and coefficients that need to be determined, obviously the time that would take for the model to execute will be much higher, right? So how many nodes I require, first of all, how many hidden layers I require, how many nodes I require in each of the hidden layer, all that is probably in the back end, you will do a kind of a loop and try to create some such kind of best practice. But otherwise, in a real world, if you have to implement this, it may take a good amount of time. In non-explainability scenario, how we can establish accuracy? Now you think of it like this. So that is the reason we are relying a lot on training data and testing data. We are doing the hyperparameter tuning, cross validation. These are all the things where we are focusing more on when it comes to providing a solution. Right? We are see there could be a lot of problems where only predictability could be a more important thing. So in that case, it may not be a big deal for us, right? So that's where we are assuring the goodness of it by using all these cross validations, hyperparameter tuning, right? And probably doing the training and testing data, evaluating the performance on the testing data. All these are straightforward kind of mechanism that we are doing to establish the accuracy of the model. Right? The explainability, obviously, in many machine learning models, right? Especially this one neural network based support vector regression or support vector machines. So in all these cases, it becomes very, very difficult to bring in the explanation. They are all more or less black box models. Even random forest, you just think about it. So there might be a feature called variable importance in each of them. But again, just like the way you talk of in a logistic regression or some kind of linear model, okay, the coefficient is positive, coefficient is negative. You can very well say whether this particular variable is affecting the output in a positive way or in a negative way. Whereas when it comes to decision trees, random forests, etc., you cannot bring in that because the way they brought in the variable importance is a slightly different pattern. So it cannot tell you whether this variable is affecting your output positively or negatively. It can only say that this variable is an important variable. So whereas when it comes to neural networks and all, people are working on some alternatives in terms of bringing variable importance, but definitely that is not a straightforward kind of a mechanism, right? So the variability, I mean, the variable importance is being worked out in a workaround kind of fashion, but it is not a straightforward exercise. That is what I can tell at this moment. All right. So let me move further. So which means if you see, you will do exactly the same thing again. You can import your MLP classifier, which is what is your multi-layer perceptron. So again, wherever you are seeing this classifier, you can also see a regressor with the same name. So when your target variable is a categorical variable, then it becomes a classifier. When your target variable is a numerical variable, then it becomes a regressor. Straightforward. That's the reason I said we will quickly run through our regression kind of a problem because we are using exactly the same mechanism there. So you initialize a blank model, default model, fit it on the training data, test it on the testing data. Look at the confusion matrix where basically you can print all of them again. So you can use exactly the same code that we have used earlier as well. Right? Probably you can copy the same piece of code. Let me otherwise for consistency, rather than using this, we will we'll talk about the consistency. Let me not write it like this. I'll delete this part. Okay. Okay, we'll just go ahead with this. I think one I wanted to retain. Right, we'll use exactly what we have used for other models. So I'll just copy what we have used in random forest and other mechanisms so that there is a consistency. Let's say whatever we have implemented in gradient boosting, I'll use exactly the same piece of code. So we'll make the change. I'll tell you how we are making the changes. I'm just copying all these pieces of code so that we'll be consistent for all models. So I'll paste these here. Same thing we can do for naive Bayes as well. I'll paste them here. Okay, we'll make the changes. So this is what you can do. Okay. So we will say MLP classifier. Okay. Then we are fitting this to the training data. Okay, I think we need model, not C model somewhere. Okay, it will give you an error. Okay. All right, so it's an MLP classifier. You model it on the training data. So we get an accuracy of 88.93%. Then you take it to the testing data. You print out the accuracy, balanced accuracy. We discussed all these things. F1 score, precision, recall, confusion matrix, Cohen's kappa, area under the ROC curve. All these things we discussed in depth. So I'll print them. So it looks like I'm getting an accuracy of 85% on the testing data. 60% is my balanced accuracy and so on. Right? I can very well look at, so I don't need this. So I can do a hyperparameter tuning. So here, what are those hyperparameters? Probably you can very well, so here, these are my hyperparameters. Well, I'll talk about them. Right, let me just copy this part. This is what are my hyperparameters. So I'll adjust those. So rather than keeping these as these are the hyperparameters for gradient boosting, I'll use these. So if I told you earlier, one is my activation function. We have discussed about it. So the activation functions are, we have an identity activation function. Identity we have already talked about, which is keep the value as it is. But I have talked about these three activation functions. One is logistic. I talked about how the transformation happens under logistic, hyperbolic tangent, and rectified linear unit. Then the learning rate. So we said at every layer, you take the error y minus y hat, multiply it with the learning rate, and then multiply it with the x value. So we are keeping the learning rate as constant, or you can keep it as inverted scaling value, or it is adaptive. So depending on, so the learning rate can be dynamic as well. And the learning rate initial value, especially when you are going with adaptive, so you can very well provide your initial values for the learning rate. And the shuffling of the observations is one more hyperparameter that it takes. So basically, 4 into 3, 12 into 3, 36 into 2, 72 models are going to be created. Obviously, it may take a lot of time, and that is where I might very well focus on only a subset. So when I want to look at only a subset, I have already talked about, we'll not use the grid search, we'll use the randomized search. We'll not use the grid search, we'll use the randomized search. And by default, I'll have only 10 models taken out for randomized search. So let us see. Let us see what is going to happen in this randomized search. So we are doing a randomized search, one based on accuracy, one based on balanced accuracy, and one based on the area under the ROC curve. 3 different models we are going to fit. Right? We are saying fit using the accuracy, fit using the balanced accuracy, fit using the area under the ROC curve. So once the 3 models, once the 3 sets of models, in each model, 10 different models are typically created because we said randomized search. So randomized search typically shortlists 10 different criteria, 10 different what you call parameter sets. And so these are the parameter sets that we have created. So one from this group, one from this parameter, one from this parameter, one from this parameter would be randomly picked like that. 10 different combinations will be selected. And based on that, it will see which model is the best or which combination of these parameters is the best when you look at it from the perspective of accuracy, when you look at it from the perspective of balanced accuracy, and when you look at it from the perspective of area under the ROC curve. So basically, many a times what could happen if you run these models in the class, this is what could be the time that it could take, because each of them, they have their own limitations in terms of the time, right? Some models like naive Bayes, logistic regression, etc., they may run very fast. But when we are trying to run these neural networks, support vector machines, etc., they are going to consume a lot of time. Right? Sometimes it gets, it may go into a few hours also, because the number of variables that need to be determined will be very heavily changing. Okay, so Colab Pro could very well be a decent alternative. But more than that, you can rely on Jupyter Notebook. If you want to go to the extent of Colab Pro, then probably you can still move towards Jupyter Notebook, right? But Jupyter Notebook, you have to be slightly comfortable with respect to the installation, etc. Colab Pro obviously is a very what you call cloud-based environment, right? But having said that, I mean, in a traditional organizational kind of an environment, probably Pro might still be a good choice. But as an individual, if you want to go to a Pro, then probably it's a personal decision. Right? I mean, on the other side, you can very well use a Jupyter Notebook as well. Just to avoid the installations on your machine and probably trying to work on your code from anywhere, anytime, that is where probably these Colab and all will come into picture. And definitely from that perspective, it's a very definite value addition as well. So the accuracy-based model fitment is already done. Now it has moved towards the balanced accuracy-based fitment. But I mean, this is the same piece of code. What I wanted to tell you is it's the same piece of code, only the model is what we are changing. And that's how you can keep continuing throughout. So let it quickly execute. I think the second one it is doing. In the meanwhile, anyone is having any kind of questions, we can discuss on that. Okay, let it execute the balanced accuracy. So this is where some time typically goes out, but just wanted to show you that if you have to run a new model also, because if you look at the scikit-learn's library, so we have talked about a few models. So in the linear, we have really looked at logistic regression, right? GLM, perceptron. So these are the algorithms that we have right now looked at, and probably in the regression we have already talked about the ordinary least squares, the ridge, lasso, elastic net. These are some of the methods that we have discussed. But of course, you could see that there are a few other linear models. You can also talk about, let's say, linear and quadratic discriminant analysis kind of model. So if you see in support vector machines, we talked about support vector machine classifier, right? But the same way you can use regressor. Now, similarly, stochastic gradient descent classification. We did not do this. So probably if you want to do it, just copy the same piece of code, right? Nearest. So if you can look at for classification problems, right? So you could see support vector machines can be used for classification. Stochastic gradient descent can be used for classification, which we did not use. Online one class SVM can be used for classification, which we did not use, right? And probably you could see linear discriminant analysis, which we did not use. Nearest neighbors we have used. Nearest neighbors classification we have done, right? Nearest centroid classifier is there, which we did not do. So let's say you want to try those things. Gaussian process classification, we did not do that, right? So if you want to bring that model, the process is exactly the same, right? Probably you can try that out as well, right? Decision trees, we did the classification. Naive Bayes, we did the classification. Naive Bayes is only for classification, so that's where you don't have separate classification and regression kind of solution. Then ensemble-wise, we had voting, but otherwise we have discussed about gradient boosting, right? We have talked about AdaBoost, we have talked about gradient boosting, we talked about random forests. So there could be a few other kinds of models, and probably there could be a lot more models that can come up in future also, which might go. So neural network classification, right? So you can so there we are talking about the multi-layer perceptron. But you can very well think of this neural network classification. So you could see here MLP classifier. That is what is a typical neural network based classification. So all of them, they work in the same way. The mechanism of execution is exactly the same. Okay, now it has done the second one and it has come into the third one. So let it complete. But what my suggestion is, you could see here there are so many algorithms that are there, right? We may have dealt with some of the most common ones. But let's say you want to try the others. It's a simple matter of copy and paste. Copy this entire block of code, make the necessary modifications, and that would still suffice your output. Okay. Okay, so it is done all three using all the three metrics. One using the accuracy, two using the balanced accuracy, and three using the area under the ROC curve. So we are trying to see which is the best combination under all three approaches. You could see under the maximizing the accuracy category, it is saying shuffling is false. Learning rate is 0.005. Adaptive learning rate and identity activation function. So this will maximize the accuracy. Whereas when my objective is a balanced accuracy, shuffle is still the same. Learning rate initial value is 0.005, adaptive, but the activation function moved to ReLU. So this combination of parameters is maximizing the balanced accuracy. Whereas this is actually maximizing, this combination is actually maximizing the area under the ROC curve. Let's say my objective is to maximize the accuracy. So I will use this particular model and I'll do a prediction on the testing data. So this is the one that will maximize my accuracy on the testing data. So what is the accuracy on the testing data? Let me see with that model. It is 85.64%. That is the maximum accuracy that this model is able to achieve. But let's say if my objective is to, so here the balanced accuracy is only 53.24%. But if I want my model to maximize the balanced accuracy, not the accuracy, then I will say, instead of using this model for prediction, I'll say more predict on the testing data using this model. So this should increase my balanced accuracy. Accuracy might go down, but balanced accuracy might go up. So you see from 53, it has become 59.53. Because my objective was to maximize the balanced accuracy. Now in that case, the accuracy has gone down to 82.5. Earlier, the accuracy was almost 85 point something. But now it has come down to 82.5. So depending on what is our objective, we might very well go for that appropriate approach. Right? So we don't need this. So this is how any model that you are picking up, right? Any model that you are picking up, this block of code will remain the same. So you can very well work out on various models, and you can very well see what is the goodness of it of each of them. So I think I think we have covered the multi-layer perceptron as well. So the final topic that I want to bring in here is the concept of pipeline. Right? That will complete our classification problem. So pipeline is nothing but series of, it's a series or sequence of, you can very well say, your scikit-learn function. So it's a sequence of your pipeline. I mean, pipeline is nothing but you are applying, let's say, some kind of, rather than typically you are talking about, you want to do some kind of scaling on the data first. Then you want to apply some kind of a box-cox transformation on the data. And after that, you want to fit different models to the data, right? So you are doing some data pre-processing, and so then you are doing some kind of model fitting, etc. Then obviously that is where you can take the help of this pipeline. So you can write one single block of code, and so rather than writing out each of the models separately, right? Because when you are actually building a machine learning model, so it's just not about choosing the right algorithm. So what we have done till now is we have run different kinds of algorithms. We have looked at what is the accuracy, balance accuracy, coherence kappa, various such kind of metrics on the different algorithm. So we have chosen the algorithm, we have looked at the hyperparameters, we have tuned them, right? And along with that, we have done a lot of work in terms of data. Initially, before we started our model, we did a lot of effort with respect to our data. We did a lot of data cleaning, we did a lot of data pre-processing, and we have also come out with a lot of feature selection kind of mechanisms as well. Right? So the model experimentation, the algorithm experimentation actually started lot after the working with the data. So when you're talking of so many pre-processing steps, they can really overwhelm your workflow. And because of that, it might become very, very difficult to track also. Right? So when we are talking of pipeline, we are simply to put a kind of an integration of building a model. So that is where we talk about pipeline as a kind of a connection. So, I mean, if you are not comfortable with pipelines, it does not harm you or affect you, right? So you can very well say, if I have to probably define a machine learning pipeline, right? Obviously, different people have different ways of defining the same, but I can look at it as a collection of steps. So it's a collection of steps that you are doing in one single go. So basically, all kinds of pre-processing steps, which are a part of your scikit-learn library, and also your model algorithm. So you can very well say it's a combination of these two things, your pre-processing steps and model algorithm. So whatever is your input data that is there, that input data is actually going into a pipeline. So first it will have some kind of pre-processing, whatever scaling, all the various activities that we call as a part of pre-processing. And that data will be taken towards various algorithms that you are giving. And that is what will give you a final scoring. So that is what we typically call as pipelining. So for that, what is that? You just see what we are trying to do. So we are importing all the necessary functions that we require. You see here, these are the pre-processing standard scalar. We have done all these. So standard scalar, which is nothing but Z value. Min-max scalar, the max, the value lies between 0 to 1. We are using train test split, k-fold cross-validation, right? We don't require the stratified fold. Then cross-validation score, grid search. These are all your metrics. Classic confusion matrix. We have discussed, now the confusion matrix name got changed, right? So let me use this confusion matrix. No, confusion matrix is still fine. So accuracy score, Cohen's kappa score. These are the various metrics that we are going to use to evaluate different models. Then this is what is a pipeline. And from here, all are my various models. So I want to use logistic regression, decision tree, k-nearest neighbors, probably a linear discriminant analysis, Gaussian naive bayes, support vector classifier, radar boost, gradient boost, random forest, MLP. If we have forgotten something else also, you can very well include in this list. So these are all the various models that we have built. So now you could see here, I'm building a kind of base model for all. So I'm creating a list of all the models in this one function called get base model. So I will just call this function. So which means it will, so initially I'm creating a blank list of base models and appending. So logistic regression with no, I mean, initially so if I have to choose between various models to start with, I can list out the default implementations of all of them. Logistic regression, linear discriminant analysis, k-nearest neighbors, then the decision trees, naive bayes, support vector machines, ADA boost, gradient boost, random forest, MLP, and if we have missed out something also, we can very well add. So these are all the list of models I am saying get one by one. Then another function is typically defined. Okay, so we can very well go with, okay, I think the stratified k-fold I have used here. So here, this is where we are getting a list of all the base model. Then the second function that we are defining is, we are trying to see what is the score. If you look at, so we are all the models we are passing. For each model, we are looking at the accuracy. Now again, it depends if I want the accuracy or if I want the balanced accuracy. Let's go with the balanced accuracy otherwise. So so the scoring will be done based on the balanced accuracy instead of accuracy. I want to find out which model will give me the balanced accuracy. and I'm testing it based on a 10-fold cross validation. So we are splitting the data based on, we are doing a stratified sampling of the data. We are fitting them, each of the models, right? We will fit the model. Model is coming from where? It's a for loop. Model in models. Models are nothing but we will call from this get base model. So this is going to append all of the results. So this function you can reuse, where we are saying what is based on the balanced accuracy, because we have given the scoring model as balanced accuracy. Now what is that we are saying? These are just the two lines that we are running. One is get base model. So first I will get this list of all the models. So if you want to add a few more models, you can simply add them to this list. But this is what will give me the list of all the models. So they will be stored as models. Then we are looping model in models. So first, the first model will be taken, which is the logistic regression model. Then the linear discriminant analysis will be taken and so on. Right? First, let's say it's a logistic regression. My data will be my data will be created into 10 different folds. I can do a cross-validation score by choosing the model, training data, X values, training data, Y values, 10-fold cross-validation, and using the balanced accuracy as a scorer. So those results are typically being appended. So if I run this, let us see. We will also, because this is going to do a cross-validation, you already know in a 10-fold cross-validation, each fold will get a different output. So you can very well find out what is the level of standard deviation across all the outputs as well. So we are trying to fill that, fit that. So you could clearly see here, the linear logistic regression is giving a balanced accuracy of 54.5. Now, for this problem, you could see that when I want my balanced accuracy to be the highest, I could clearly see that for this problem, naive Bayes has given me the best possible result when it came to balanced accuracy. Right? This is the one that has given the maximum balanced accuracy. Of course, some of the models are taking slightly more time to execute. But when it comes to accuracy, probably there might be a different problem altogether. Okay, the neural networks also have come closer to almost 60%. But the best model came from the perspective of naive Bayes. But when my problem is about accuracy, not the balanced accuracy. Let us see. If my problem is about accuracy and not balanced accuracy, let us see, the results could be different. The best model now, naive Bayes is no more the best model, at least now we could see. So depending on what is the metric that we are interested in, also the best possible model could differ. So here we could see probably the best model is coming in terms of gradient boosting, looks like 84.97%. Right, that is the model that has given the highest accuracy on the testing data. Right, but again, compared to the accuracy, probably we may want to go with the balanced accuracy itself. Right, so that is what you could see as a difference. You can bring all the models in one single shot, and even you can bring in some kind of pre-processing. Now that is where I am bringing in the pipeline. So you could see here we are using the standard scaler or something. So one function is you take the scaled model. So you could say if it is standard, then we'll take a standard scalar. Min-max, you will take a min-max scalar. Or if it is something else also, you can very well bring that in. So now again, I'm trying to add all of them to the pipeline. Initially, I'm creating a blank pipeline. Now you see the scalar. So whatever is the name of the scalar, we are going to append it. Obviously, then it would become a standard scalar or something like that. Then we are also putting another pipeline wherein we are saying scalar and logistic regression, scalar and linear discriminant, scalar and KNN. So we are adding multiple such kind of models, right? We are taking the name of the scalar, standard scalar, plus whatever is the model that we are going to go with. So basically here, we are appending all of them. So all the models along with a scale, right? All the models along with the scaling is what we are typically creating as a pipeline. So, and we are appending all those pipelines. Okay, so which means there are different models that you are building. Now you can again run get the model, get run. So here, let's say we are calling it based on the min-max scalar. So based on the min-max scalar, if I am running, so basically the name of the models, we are simply calling as name of the scalar plus this. And the pipeline we are typically creating as these two steps. Now, if I want the third step, okay, let it run. So when we are doing a min-max scaling and then running the different models, it looks like the best model is this one, 85.04 gradient boosting has given a higher level of accuracy than the earlier scenario. Earlier gradient boosting was the best, but it has given only 84.97% accuracy. But now it looks like after doing a min-max scaling, it has gone to 85.04% accuracy. So sometimes you may want to do the various steps, right? Probably here I may want to add one more dimension out here, right? Let me talk about. So the third step that I may want to add here, right? So we will add, once you do this, we'll call it as a EO-Johnson transformation. Let's say I want to do a EO-Johnson transformation also of the data, right? So that way, what could very well happen, we will have to bring in the EO-Johnson. So we'll have to first import this. Right. So we'll import this transformation. Right. Then depending on where you want to put that, let's say here we will say non-linear transform. Okay, we'll say non-linear transform, and we'll have to use this power transform. We'll use this power transform. Right. So this part, let's say, I can even put before or after. So that's fine. We'll keep it here. Right? This step, let's say, this is an extra step. So which means what I'm saying, initially do a scaling, then you do a nonlinear transform, then you apply the model. So we are saying 3 steps, let it do in one single shot. Right? Rather than we doing all the steps separately, right? We can very well ask the system to typically take care of something like this as well. So I'll put it here, right? So if I try to run here, and let's say we'll continue with the min-max scaling itself, followed by a power transformation, followed by the running of the model. So let us see. Okay, all 10, okay, because it has got converted into 0, 0, 0. The model is misconfigured, or otherwise, let me put them before. Let me just try running this. Okay, in baseline 2, I did not give the model, but that's okay. All right, let me look into this again before I give it as an updated code to you. Let me simply come back to you on this. But whatever are the modifications that whatever are the series of steps that we want to perform on our data, we can very well go ahead with all the steps. That is where the pipeline is coming into picture, right? So I'll just update this code with this nonlinear transforms also, right? Probably somewhere I made a small mistake, looks like. But right now, let the code be completely working. So you could clearly see now the various models are typically getting executed. And in each of the cases, we are getting different results. Okay. So I think there was a question. We need to process pipe. No, no, no. Basically, the pipeline is, even you can pass in the hyperparameters also. Yes. See, the first thing is you have finalized which models, which parameters for each of the model is the best fitting parameter. So what you can very well do, instead of just giving this as a blank, you can pass in those parameter values into each of these functions. Then what can very well happen is, instead of every time it doing the hyperparameter tuning, identifying the best possible parameter combinations, etc. Right? So here, let's say in case of neural networks, we got, let's say this is the best model that we have got, right? I'll just give you an example. In the neural networks, let's say this is the best combination that we have got based on balanced accuracy kind of a mechanism. So when you are defining your MLP classifier, you simply give this as your parameter. Right? You can very well specify the parameters for your model. Or initially to get a broader hold of various models, which one to start off at least. So take the base model for all of them, whichever is the one that is giving the best result. So probably it's in this case, let's say the GBM is giving me the best result. Then I will do a hyperparameter tuning only for the GBM model. So these are the two different ways in which people work. One, they use the base models in the pipeline to identify which base model has the best utility altogether. Then they tune that model only. That is one way. Second, you try all the models with tuning, find out the best combinations of each of those models, and put all of those best combinations into your pipeline. But that one is more beneficial only if you are running these models almost every day, rather than trying to run each model and hyperparameter tuning every day. We will only run the best out of all those models on a regular day-to-day basis. So these are the two different applications where you can use the pipeline. All right. So with this, we are almost done with the end-to-end of classification. I'm sure you can take this piece of code, try to work it on some new data sets, right? And probably we can start discussing on what are the gaps, right? Probably right now this entire data set is working very well. The entire piece of code is working very well, because I simply did a run all and it was working till end to end. So in case something is not clear, you execute it end to end. In case something is not clear, please bring it to my notice. Okay. So that is how you can very well learn. This is a complete end to end case study for classification. Right. I hope, probably I typically find this is more and more detailed. So I will share this one today. Right now that we have done, I'll share this completely. Okay. All right, then I'll just share it once we are done. I'll share it in the WhatsApp group. Thanks a lot, everyone. You need to practice more and come back to me, and that is when I can understand where you are typically getting stuck. Yeah, thank you. See you again. Probably I'll just get back. Probably Friday is there, but I'm seeing if we can have one session on Wednesday also. So I'll get it communicated across. Yeah, thank you. Take care. Bye-bye.